Okay, hello guys. So today I'm just going to talk about an interesting lemma that I came across while I was going through my matrix analysis course. Um, so, so this is a course that I did during my university days, and I have the lecture notes with me. So I was just going through the notes, and then I saw this interesting little lemma, which I thought I can just put it here. And so let's look at the lemma, right? So let's say you have uh, two vectors, right? So x and y. The two vectors are in, let's say, the vector space formed by this complex number c to power n. That means it's uh, all the elements are n tuples, right? With entries complex numbers. Now let's assume that the norm of x is equal to the norm of y, right? That means they are of the same length, right? They are of same length. So this is norm, right? And when I say two, it's Euclidean norm. That's what I'm calculating, right? It's a Euclidean norm. Um, and so let's say this is positive, right? Now the lemma states that if you have any two vectors in this vector space, uh, what you have is you can actually form a unitary matrix, or in other words, there is a unitary matrix. Let's denote it by U, and let's also give this kind of notation indicating that this unitary matrix is formed by it depends on x and y, right? It is specific to this x and y that we have now. So there's a unitary matrix which is just going to transform your x to y, right? It's just going to do a linear transformation on x and take it to y, right? So this is the lemma. So the lemma states that there is a unitary matrix which can do this, right? Just to recall, unitary matrix means a matrix U uh, where you can so it means when you do U star and you multiply by U, it's going to give you an identity matrix, right? So U star means you're taking the conjugate and then transpose, right? So if you have a matrix ABCD, right, all complex numbers, then if you're taking the star operation, what's essentially happening is you just take the conjugate, right? A star, D star, uh, C star, and I mean A bar, D bar, C bar, and B bar, but then you transpose it. So this comes down and this goes up, right? So this is what I mean by taking the star operation on a matrix, right? So it's interesting because with this you can prove things like LR decomposition, right? Uh, or sorry, LU decomposition. So you can actually prove some decomposition theorems which are really interesting. So let's see how we can prove this, right? So the proof goes like this. So let's write this down. Proof. So there are two cases, right? So because these are two different vectors, either there is, you can write x or let's say y instead of x. Let's write this as y. So y, either y can be written as e to the power I theta x, right? Where theta is some angle or it's in a real number space, right? It's in real line, right? Uh, so either this happens or this does not happen. That y cannot be written as e to the power I theta x, right? Either one of them, right? So there are two cases. We'll go step by step. So let's take this first case. Let's assume that you can write y as e to the power I theta x, right? If you can write it like this, then things become much more easier. So you can very easily calculate the unitary matrix, right? okay, so let me write here, this is unitary matrix. So you can very easily calculate the unitary matrix. And the unitary matrix in this case, right, it will turn out to be nothing but e to the power I theta times the identity matrix, right? Now, so first of all, is this a unitary matrix? Yes, because when you take the U star, right, U star is nothing but identity matrix. It's all real numbers, so it stays the same. Uh, and even if you take the star of this, it's the same. But this complex number, you should just take the conjugate, so e to the power minus I theta times I, right? So that's U star. Now, when you do U star times U, what's going to happen is you just have e to the power minus I theta times I, e to the power I theta times I. Now, these are just numbers, so this gets multiplied, and you can actually cancel them, and you have identity, right? So I times I, which is basically identity itself, and this get canceled, so I can just remove this term, and what's left behind is the identity matrix. So you have this is so you can conclude that this is a unitary matrix, right? So this is indeed a unitary matrix. And so what's the other thing that we need to check, right? So the other thing that we need to check is whether we get u. So does u transform x to y, right? So it can be seen because uxy is e to the power I theta times I. Now, if you multiply x on both sides, right? So you multiply by x. X is a vector. So when you multiply it, because this is identity, you have e to the power I theta times x, right? And e to the power I theta x is nothing but y, right? So we see that this unitary matrix does transform x to y, right? So what we conclude is this particular case, for this case, this is simple. This is, it can be easily done, right? Now, so let's say, okay, so this is an easy case, right? Now, when we go to, the complex one, right? The next one, when you cannot write y as e to the power I theta times x, that's a it's a little bit involved, right? So we'll go step by step. Okay, so for this case, so what's the case here? So y is not equal to e to the power I theta x for any theta in R, right? So if you check all possible theta in R, none of them will satisfy this relationship, right? Okay, so that's the situation that we are in. Now, for this case, the goal is to construct that unitary matrix, right? So what is that unitary matrix that's going to transform x to y, right? So so for this case, what we're going to do is we are going to do this x star y, right? So remember x star y, right? When you do this operation x star y, it's basically a number, right? So for you to visually understand this, the convention that we are going to use, right, is all our vectors are going to be written like this, right? It's going to be vertical, right? It's a column vector, right? Like this. So it has components y1, y2 till yn, right? So we are going to assume this all of them are column vectors, and the reason for doing this is because so x is again a column vector. When you take the conjugate and transpose, this will become a row vector, right? x1 bar, x2 bar, xn bar, right? All the xi's are complex numbers, so you just take the transpose of it, so that means it becomes a row vector, right? So now x star times y, right? So let's multiply y here. So that means you're multiplying by a column vector, which is y1 till yn. Now you can see that this is nothing but x1 bar y1 plus x2 bar y2 plus etc. plus xn bar yn, right? Now, this is just a number. This belongs to the complex number, right? So it's a number here, right? So that's what we see here. So let me erase all this. This is just to show you that this computation will give you just a number. Okay, so x star y. So what can we do here? So x star y is a complex number. So what we know about complex number? So complex number consists of two parts. One is the absolute magnitude of that complex number, right? So you take the absolute magnitude of it. And then there's this e to the power I phi, right? So this is basically the magnitude of that. Okay, you can think about this as a vector in the space Cn, right? So the magnitude of that, and then there's this component e to the power I phi, right? Uh, I'm sorry. So sorry. X star y is a complex number, right? So it's an complex number, right? So any complex number has the absolute magnitude of that complex number, and then you have this e to the power I phi part of it, right? Which will indicate the direction in which it lies in the complex space, right? So what I'm talking about is if you have um, the complex space, right? It has the real part. So let's say x and y, right? So any complex number is of the form x plus iy, right? So it will have the x direction and the y direction. So you have your complex number represented here by this vector, right? So for this vector, you have this absolute magnitude of this vector, right? Absolute magnitude of this vector here. So this is, let's denote it like this. And it has an angle phi, right? So this is nothing but the absolute magnitude of v times e to the power I, this angle phi, right? So these are both the same thing, right? I just have written it in a different so this is I have introduced an angle into this particular uh, equation, right? But they are the same thing. Okay, right? So now what do we see here? So x star y is this. Now what I'm going to do is so the proof has already started here. Um, so let's define this, w. So w is e raised to I phi, right, times x minus y, right? Now, what's the motivation for this, right? What is this w? How did I get this w? So remember, we started off by saying that y is not equal to e to the power I theta x, right? Um, and so it is also, this implies that y is also not equal to e to the power I phi x, right? For this particular phi here, right? Phi is in a real number. It's a real number, right? So this is the case. So you can write omega or w, right? Or let's say omega here, right? Is e to the power I phi x minus y. Now, what is that unitary matrix? Right? So the unitary matrix will turn out, it will turn out to be e to the power I phi times the identity matrix minus 2 omega omega star divided by omega star omega, right? It turns out this is the unitary matrix that's going to do this transformation, right? Which is going to take your x to y, right? So first thing, how do we prove that U is a unitary matrix, right? So um, so what's the first thing that we need to do here? So we need to calculate U star times U, right? So what we need to calculate is U star times u, right? So first let's start with u star. So what's u star? So this is a complex number. You just take the conjugate of that, right? And this is a matrix, right? So if you need to take the conjugate, you need to take the star operation for this. So for identity matrix, it remains the same. For this one, right, when you take the complex conjugate, right, it stays the same, right? The reason being, when you take the conjugate of this, right, when you take the complex conjugate of this, it will turn out to be this. That is, this will be omega star star times omega, right? So this one, you just do the star operation for this whole thing, and it comes forward, right? And then this, you take the so you take the star of this, and it goes back, right? So when you take a star operation, if it's a and b, right, b star times a, that's what happens. So it gets flipped, and you apply b star, and then there's a. So the same thing I'm doing for w star. So now let's take the complex conjugate for this, or the star operation for this one. Um, so when you do this, you get w, right? W star star, it's the same thing, and then you get w star, right? So what you end up is the same thing, right? It hasn't changed, right? So same is the case with w star w, right? For w star w, it will turn out when you take the star operation, you can check it will be the same. It will stay the same, right? So because of this, what will happen is you just it just stays the same. So this quantity remains the same. Okay, so now let's move down a little bit. Okay, so let's calculate u star times u, right? So this is nothing but e to the power minus I phi I minus 2 w star w star w, and then you have e to the power I phi, and basically the same thing, I minus 2 w star divided by w star w, right? Now what will happen is this term and this term, these two complex numbers, they are conjugates of each other. When you multiply them, it will become 1, right? When you multiply them, it will become 1. What's left behind is this matrix and this matrix, which when you multiply, what's going to happen is, so I times I is identity. I times this term will become minus 2 w star divided by w star w. It's the same thing. And then this term multiplied by the identity will become 2 w star divided by w star w. And when you multiply these two terms, it will be 4 times w star, and here's another w star divided by w star w. Um, so there's one more term, the same thing, it gets squared, right? So it's basically the square in the numerator as well, right? The omega star the whole square. But I have not done that. The reason being, you will see why I did that. So what I'm going to do is, now this is nothing but I minus these two are the same thing, so just add it up, 4 w star divided by w star w, and then you have 4 times this term. So what do we have here? So you have matrix w star, and then matrix W, W star. So when you multiply W star and W, right, when you multiply W star and W, so W star W, right, this is a number, right? This will turn out to be a, okay, so I think there's a little bit of a correction needed here. So the W that we started with, it was this one, right? So it was e to the power I phi x minus y. So it is not a matrix. It's just a vector, right? It's just a vector. It's not a matrix. So my bad. But going down, so you can, so what I'm doing here is a vector W, W star W. So W star W, right, when you will calculate W star W, it will turn out to be a complex number, right? This term, right, so remember we started by saying that W is a column vector, right? So W star is a row vector. A row vector times a column vector is going to give you a complex number, right? It's just going to be a number here, right? So because it's a number, you can just pull it out and you have W star W, and then you have W W star, right, divided by W star W, the whole square. Yeah, and I also realized that I've changed the, so I was calling this omega a few moments back, but then I've changed it back to saying it to be W, but it doesn't matter. So um, ideally, the way I have written this is it looks like omega, but you can also think of it like to be W, right? Um, Anyways, so W star W and here W star W square, so it get canceled and just you're just left with one of them, right? So let's erase this. So what you have is this 4 times, right? So you can see these two get canceled and what you're left with is the identity matrix. So this is nothing but it's a unitary matrix, right? So the matrix that we created, right? The matrix, this time I'm correct. It's a matrix. So this is a matrix, right? That we created is, turns out it's a unitary matrix, right? So only thing that's left is for us to show that it transforms X to Y, right? Which I will do in the next notebook, right? Okay, so we need to prove that the unitary matrix uxy given by e to the power I phi identity minus 2 times w star divided by w star w. This is just the transformation or the matrix that we are looking for. Basically, it's going to transform x to y. Now, for this, what we are going to do is, so this is the part B of our proof. So what we are going to do is we are going to calculate this term W star W, right? Basically, we are going to calculate the numerator and the denominator terms, right? So the numerator will be a matrix, denominator will be a number, is a number. Actually, you can just check W star W is just a number, this is a matrix. So the I'm starting with the denominator part. So let's calculate this. Remember, W was the way we defined it. It was e to the power, right, I phi x minus y, right? This is the, we got this from the assumption that x cannot be written as, or y cannot be written as e to the power I theta times x for any theta. In particular, for this phi, you don't have equality, so this is not zero, right? So W star W, right? W star means just take the conjugate, right? So conjugate transpose. So e to the power minus I phi x star minus y star times e to the power I phi x minus y. So this is nothing but when you do this multiplication, you have e to the power minus I phi, e to the power I phi gets cancelled. You have x star x minus e to the power minus I phi x star y, minus y star x. Now e to the power I phi comes in the front, and you have plus y star y. Okay, so you have this. Now we need to do a little bit of algebra here. So if you remember the way okay, it can be difficult for you all to remember the phi, right? The how we did. So you may have to go back in the a little bit before in the video where I defined how did I arrive at this phi thing, right? So the way I arrived at the phi was x star y, right, is equal to e to the power I phi times absolute value of x star y, right? This is the place from where we started this whole thing, right? Um, so so by looking at this, we can do certain things here, right? So for example, this one, right? So okay, let's keep this in the box. So x star x, and let's group together this y star y with x star x. And then you have e to the power minus I phi x star y. X star y is nothing but e to the power I phi times absolute value of x star y. Now, e to the power I phi and minus e to the power I phi and e to the power minus I phi get cancelled. So you have absolute value of x star y and minus e to the power I phi y star x, right? So what's y star x? So let's calculate this. So y star x, the way you get this, uh, so the way you get y star x is just by taking the star operation on this one, right? When you take the star operation on this one, you get y star x. Okay, so this is nothing but e to the power minus I phi absolute value of x star y, right? So because of this, what we have is so what you have is y star x. Instead of y star x, I can just say this is nothing but e to the power minus I phi times absolute value of x star y. But these two get cancelled because they are just conjugates of each other, right? So you are left with minus absolute value of x star y, which basically you can group them, right? So you can group them. So let's put this in the box as well. So you have x star x plus y star y minus 2 absolute value of x star y, right? Now, the way we started this whole thing, right? If you go back and look at the lemma, we said that your x and y have the same norm, right? It has the same Euclidean norm, same uh, L2 norm, right? So L2 norm is nothing but, so basically, if you take the square of this norms, it's the same thing, right? If you started with something which is equal, if you take the square, it's again the same thing. But when you take the square, it turns out this is nothing but x star x, right? And this turns out it's nothing but y star y, right? The reason being, the norm, the way you define norm is nothing but square root of x star x, right? For any vector x, this is how you define it, right? And so from the definition, it follows that when you square it, you get x star x, right? So from here, what you conclude is that, so let's, I think we can erase this part. So what you get is that these two terms are the same, right? They are the same thing. And let's denote this. So you can add them and you can say it is 2 times x star x. You can also say 2 times y star y, but let's keep it x star x. So you have, and the rest of the term x star y, right? Okay, this can be a little confusing here. Like I should be putting this here. Okay, so you have this, right? Now, this is w star w, right? Now let's try to calculate what's w star x is going to be, right? So what's w star um, x is going to be, and the reason being, you will see if you calculate this one, uh, there's something interesting going to happen. So w is nothing but e to the power I phi x minus y. So when you take the conjugate, or when you take the star, right? When you take the star, because e to the power I phi is just a number, you just take the conjugate of that. You have x star minus y star, right? And then you have x. So this becomes e to the power minus I phi x star x minus y star x. Okay. So this is what you have. And from here, what you can make out is this one, so uh, so the way we started this, or basically this one, right? This particular equation that we have here, we can use it, right? We can use it here, and instead of y star x, you can write e to the power minus I phi absolute value of x star y, right? That's done. So you can just substitute here, and then you can pull out e to the power minus I phi. So when you do this, what you get is x star x minus absolute value of x star y. And so what is this, right? Now this one, right, if we go back, so if you, it's here, so this one, right, x star x, so 2x star x minus 2x star 2 times absolute value of x star y, you just pull that 2 out, right? So, and the whole thing was nothing but w star w, right? So we started with saying, okay, this is w star w, and you get this. And so what we can do here is basically, what you can do here is basically e to the power minus I phi. This is w star w divided by 2, right? So that's what you get here. Okay, so this is a lot of algebra, but now you will see everything comes together and it gives you the result, right? So you what you do is uxy, right? When you apply on x, this is nothing but, so the u is e to the power I phi times identity minus 2 times w star divided by w star w, right? And you apply on x. So when you take your x inside the brackets, what's going to happen is e to the power I phi, right? This becomes x minus 2w, w star x, right? W star x is nothing but this whole thing. So let me write this here. So e to the power minus I phi w star w divided by 2, right? And in the denominator, you have w star w. So you can see that they get cancelled, right? This term and this term gets cancelled. And so it gets cancelled. So let's just erase them. 2 will get cancelled as well, 2 and 2 here. And so what you're left with is x minus w times e to the power minus I phi, right? So now what we can do is, let's try to, so e to the power I phi x minus, now this term, right? So this one, this is nothing but, you can derive this. So w, the way we defined w was e to the power I phi x minus y, right? So then w times e to the power minus I phi is going to be nothing but x minus y e to the power minus I phi, right? So putting this here, this is nothing but x minus y e to the power minus I phi, and you can cancel your x, so you have e to the power I phi and y e to the power minus I phi, right? And you can see that these two get cancelled, and what you're left with is y, right? That's the end, right? So a lot of algebra, but at the end you can see that this matrix U, which we proved that it's a unitary matrix, will take x to y, right? And that's it. So that's the matrix that we were looking for. So what do we conclude here, right? We conclude that the lemma is true, right? That if you're given two vectors x and y in Cn, right? Cn, by that mean the vector space formed by complex numbers, right? N tuples of complex numbers, right? If you have any two vectors, if the norms are the same, then you will always have a unitary matrix which is going to transform x to y, right? It is always guaranteed. So there's a unitary matrix which can transform x to y. Now, I will also say before I close this video here that if, let's assume that your x and y are in Rn, right? Rn means they are not complex numbers, but let's say all of them are in this vector space formed by real numbers, R to the power n tuples of real numbers, right? If x and y are in Rn, if you follow the proof, right, the way we constructed U and the way we constructed our W, it will turn out your unitary matrix U will be a real number matrix. It's a matrix of real numbers, right? So when you have x and y in Rn, specifically when you pick from Rn and the norms are the same, then that unitary matrix will be in real number space, right? So that's what we get out of this whole thing. Okay, I think that's good enough. I will stop it here for this particular video, and I will see you in the next one. Have a good day. Bye.